And next we have Tyron Johnson, Director of Solutions Engineering at Belden, who's going to be presenting on the evolution of data center optical connectivity.
Hi, good afternoon. My name is Tyron Johnson, and today I'm just going to give a brief 10-minute overview of the optical connectivity within the data center and how it's evolving in line with the increasing need for more data. So starting off with the common kind of optics in the data center space, the 400 gig pluggable optics. You have the two main form factors, which are the QDD 400, also known as the 56DD, and the OSFP. The two common things between these two form factors is that they both share at 400 gig 8 times 50 gig PAM4 electrical lanes, and then they're gearboxed into 4 times 100 gig PAM4 optical interfaces. So with the DD, it's main difference between the DD and the OSFP is the DD is two pins that are basically stacked on top of each other, and then the OSFP is one row of pins for the 8 times 100 gig, or the 8 times 50 gig in the 400 gig case. So the common kind of deployment, especially with the leaf and top of rack, is the DR4 connecting to the 100 gig single lambda optics. And the main thing to consider with the 100 gig side of the optics that they do need to be single lambda, because on the 400 gig side, it is the 4 times 100 gig PAM4. And a common mistake is that they try to connect it to the 100 gig LR4, which is 4 times 25 gig NRZ. So we get that question quite a lot. So the kind of next evolution step, next generation, is the 100 gig PAM4. So if you look at the bottom one where it's an 800 gig optic, it's still QDD or OSFP, but now it has 100 gig PAM4 electrical lanes. And then you kind of backtrack that to the 400 gig optic as well. And now you have 100 gig PAM4 electrical going straight through to the 100 gig PAM4 optical. So you're no longer gearboxing that 8 times 50 gig. You're going straight to the 100 gig optical. So it's a power saving there. So that's kind of the next leap. And then the connectivity here, as I showed previously, it was basically 4 times 100 breakout. But now you can do the 2 times 400 gig breakout. So this is more in your spine and leaf, and a lot of GPU applications are using this 2 by 400 gig breakout. So the OSFP, the top kind of optic, is a 2FR4, 2 kilometer. And one of the main things with the 800 gig optics here is that they have dual connectors in the transceiver itself. So if you go back to 400 gig, it had single MPO or single duplex LC, whereas now it has 2 connectors, so dual MPO or dual LC. So the 2FR4 on the top has the dual LC, which allows you to connect to the QSFP112, which is the 4 by 100 PAM4. I'm sorry, I'm going to say electrical lanes a lot today. And then if you go down where you have the dual MPO, because it's got dual MPO now, you can use an MPO to 4 LC twice, so you can do a breakout to 8 times 100 gig. And then they can also have the added flexibility of point-to-point. So a 2DR4 can connect to a 2DR4 using 2 MPO patch cables. There are other variations out there, which are the DR8, which is often confused with the 2DR4, but it's a single MPO 16 connector, which you do point-to-point. And again, it's very similar for the multi-mode, but the main difference is just the distance, and it uses cheaper lasers, so it's a cheaper deployment. And this is probably the most common one. One of the most common deployments for GPU is the 2 SR4 breaking out to the 2 OSFP112 VR4, especially for the InfiniBand applications. Again, it's dual MPO. So the kind of next step up is, the next generation leap is now 1.6. So they had to introduce a new form factor to fit in 16 100 gig PAM4 electrical lanes. So it's now called the OSFP XD, which stands for extra dense. but it also can be backwards compatible to do the XD8, which means it can do 8 lanes of 200 gig as well. So it's got a bit more flexibility, kind of thinking, forward thinking. So you're probably going to see a pattern here. The next kind of step up is now 200 gig on the electrical side. So this is like the next big fundamental step for 1.6 and 3.2. Again, it's just 8 times 200 gig straight through to the 800 gig PAM4 optical. And then if you backtrack it again to the 800 gig optic, which originally was 8 times 100, it's now 4 times 200. So less power consumption, more breakout options again at 1.6. And this will happen again for 3.2. And then it might happen again for 6.4. It's just going to be 400 gig electrical lane, 800 gig electrical lane if it's feasible. We may even turn to coherent light technology rather than PAM4 or even stuff like PAM6 and PAM8. So the major differences between the three form factors here with the QDD and the OSFP and the OSF-XD is the OSFP 1600 or the 224 200 gig electrical lanes has less power consumption but more thermal capabilities. It has an internal heatsink, whereas the QDD version does not have an internal heatsink. It relies on the host platform to do that. So what typically happens is OSFP is the first generation of 800 gig or 1.6, and then QDD is the next one that comes after. But as I mentioned before, they also introduced the XD, which is 16 lanes of 100 gig PAM4, or can probably for 3.2 do the 200 gig there as well. It does have more power consumption capability, so it probably is more the optimal choice for 1.6 or 3.2 Tera ZR for your DCI interconnect. And the problem is it is a larger form factor, so the NEMs have to kind of cater for that larger form factor. And just some examples again of 1.6 breakout. So it's 1.6 on the spine side, and then you're breaking out to the 2 times 800 gig now. Still keeping the OSFP form factor, and then it could also keep the QDD 1600 form factor. But the more interesting thing here is that now you can break out to 4 times 400 gig using the FR2, which is now 200 gig electrical lanes at 400 gig rather than the 400 gig electrical lanes. So as technology moves up with the electrical lanes, you can kind of backtrack each one as you go along. So one of the other big things that's kind of happening in the data center space is the linear pluggable optics, or LPO. And the main difference for LPO is it removes the DSP on the transceiver and the CDR. About 45% of the power consumption on an optic is the DSP, but it also adds a lot of functionality with the equalization and the SNR. It's a very important part of the optic. So what's left is basically the equalization chip and the amplifier, which reduces your latency and your power consumption. Is also a lower manufacturing cost versus the DSP-based solution, but there are challenges with that. The standardization is very new. We have to rely on the host platforms to support LPO. The distance is much shorter because you haven't got that DSP for the compensation, and it's also looking like it's going to be closed system links. So that was my short presentation. Was there any questions on that? Thank you.